Ever see one of those little robots zipping around a room and wonder, how does it actually know what it's doing? You know? It seems like magic, but it's not. It's math. And in this explainer, we're going to pull back the curtain on the fundamental calculations that turn a pile of parts into a machine that can actually think and move. So let's get into it.
So it really all comes down to this one simple but, incredibly complex question. For a robot to do literally anything useful, it has to first answer, where am I? This is the core problem of what they call self-localization, and believe me, solving it is the very first step towards any kind of autonomous action. Okay, so our story starts with a little component, just like this, an infrared distance sensor. Basically, it shoots out a beam of light and then measures the reflection to get a sense of its surroundings. It's a fantastic little tool, for sure, but it only gives us pieces of the puzzle. It's the math that has to put all those pieces together. To navigate its world, our robot has to solve two main problems. Think of them as two big questions that kind of build on each other. First, it has to figure out its starting position. Then, once it starts moving, it's got to keep track of where it's going. This is the big one, the global position question. I mean, imagine being dropped into a pitch-black room and having to figure out where you are just by feeling the walls. That's kind of what the robot's doing. It uses its sensors to take readings, trying to match them to a map it has stored in memory to figure out its initial pose. That's just a fancy word for its position and the direction it's facing.
But here's where we hit our first snag. See, the sensor has a limitation. During calibration, the engineers only measure its voltage output at specific, known distances, so we get these nice, clean data points. But what happens if the sensor gets a voltage reading that falls between two of those known points? The raw data has gaps.
And that's the key question, isn't it? The robot can't just stop and ask for more data. It has to make a very, very educated guess to fill in those blanks. So how does it do it? Well, it uses a really beautiful mathematical tool. The solution is a concept you probably learned way back as a kid. It just has a fancier name now. The robot is essentially playing a game of connect the dots with its sensor data, and it does that to paint a much more complete picture of the world around it. This is called interpolation. It's just the process of building new data points that fall within the range of what you already know. So by using the values it does have, the robot can make a surprisingly accurate guess about the values it doesn't. This is really the first key piece of math that lets the robot see the world. Okay, so the robot has used interpolation to figure out its starting point. It knows where it is, awesome. But the moment it starts to move, a whole new problem pops up. How does it track its path without constantly having to stop and rescan the entire room all over again? Well, the answer is odometry. It's a form of what's known as dead reckoning. See, the robot has these little sensors on its wheels called optical encoders, and they produce a pulse, or a tick, every single time the wheel rotates just a tiny amount. By counting all these ticks for each wheel, the robot can figure out exactly how far each one has traveled. Right, so counting ticks is great, but how do you turn a bunch of clicks into a smooth trajectory on a map? This is where calculus rolls onto the scene. And don't worry, this isn't scary textbook stuff. This is calculus in its most practical, powerful form. It's the engine that translates those raw wheel ticks into a path. So here's how it works. It's this crucial three-step process. First, it counts the ticks. Simple enough. Second, using differentiation, it calculates its instantaneous speed and direction, like right now, at this exact moment. And third, using integration, it adds up all of those tiny instantaneous movements over time to plot its entire journey from where it started. But here's the twist. Whether we're talking about interpolation or integration, none of this is perfect. It can't be. In the real world, with limited data, every single calculation a robot makes is a sophisticated but brilliant approximation of reality. This quote from the source material really just says it all. We're always trying to understand a continuous, true function, like, say, the exact distance to a wall, but we can only ever sample it at a few specific points. The math is our tool for building the best possible guess from that limited data. So how do we make these guesses better? Well, a simple approach, what's called a piecewise constant approximation, just takes the last known data point and assumes everything stays the same until the next one. But a smarter guess, a piecewise linear one, draws a straight line connecting two known points. You can just see how much closer that line is going to be to the real curve. And the result is, well, it's pretty striking. By using a slightly more sophisticated mathematical model, connecting two dots instead of just one, we can dramatically reduce the potential error.
No guess is ever going to be perfect, but smarter math gets the robot's understanding much, much closer to its true position in the world.
So in the end, that's what this is really all about. The robot doesn't have a map in its head like we do. The math is the map. It's the set of tools the robot uses to build a useful, actionable model of its environment from scratch. So let's just recap the robot's mathematical toolkit, right? It uses interpolation to make sense of its sensor readings. It uses differentiation to calculate its exact speed and direction at any given moment. And it uses integration to stitch all those moments together into one continuous path. What's so amazing about all this is that these incredible complex machines, things that really feel like science fiction, are actually standing on the shoulders of mathematical giants. They're built from these fundamental, elegant ideas that let them see and navigate our world. And that kind of leaves us with a final thought. The core calculus that makes all this work was developed hundreds of years ago. It really makes you wonder, as we continue to push the boundaries of mathematics today, what currently unimaginable technologies will be built on the discoveries that we're making right now?